So far we have seen how the internals of a computer, the CPU, work, right? And of course the question that has sort of been dodged up to this point is, where exactly are these inputs coming from? We talked about performing operations on certain inputs that are stored in memory. How do those inputs get into the memory, right? And how do we take out the outputs that are generated as a result of these computations? So just to quickly recap where we left off, right? A CPU, in other words, is capable of primarily three types of functions. One of them is the actual operation, the computation, right, which we sort of classify as arithmetic and logic operations. Now, to assist those ALU operations, we also need to have some memory operations, because we sort of motivated this by saying that the speed of memory would sort of keep going down as it becomes larger, or rather to build physically an electronic memory that has a large size and is also very fast turns out to be difficult. So we sort of break it into a kind of hierarchy. And what that means is we need to explicitly bring in new instructions in the CPU that handle the loading and storing of data from that memory into the core of the CPU, the part that does the computation. This is a very important aspect, and we'll make a lot of use of this feature as we move forward. And of course the third part of it was the control flow. The whole idea that we could change the flow of the sequence of instructions that we are following, right? So after performing a certain set of instructions, we could either go back and repeat the same in a loop, or that we could simply jump to a new part of new set of instructions and start executing them, right? So the control flow is the sort of third crucial aspect that builds up the core of how the CPU works. Now, in order to communicate with the outside world, how do we exactly go about this, right? And what we are going to do is to sort of use at least one of the techniques that is used, right? And that's one thing that you need to keep in mind while going through all of these discussions that we are having over here. This is one particular way by which we can solve the problem. It's not necessarily the only way of solving the problem. It is probably the most popular, the most well known, right, and the most widely used rather. And what we are going to be doing is essentially sort of creating a kind of fake memory interface, which says that rather than talking to a bag of words where we can store things and take them out later, we are going to use that as a trick to communicate with the outside world. So let's see how that happens. So once again, quickly, the CPU, right, can handle the computation aspects of what we want to do in a computer. In some sense, that's exactly what we want the computer to do, right? And we have a memory that can handle storage, right? What do we mean by storage? It means that at the end of the day, we want to perform these computations on large amounts of data. Where does that data go? Where does it get stored? How is it manipulated? And how is it manipulated? Again, the instructions, those also need to be stored somewhere, and the results of the computation need to be stored somewhere. So memory is essentially handling something that we call storage, right? As we go forward and build larger and larger computers, it becomes obvious that the basic memory where we just put data and get it out needs to be expanded in many other different ways, right? So which is why we come across disk access, network storage, and various other kinds of things that expand upon our capabilities. But for now, memory essentially is one black box that stores data for us. The question that we want to answer is, how do we get data into the memory or out of the memory? In other words, how do we communicate with the outside world, right? From a practical point of view, since at this point all of you have at some level used a computer, right? It might even have just been that you have used a mobile phone, which at the end of the day is a computer, right? You know that there is some kind of a keyboard or a touch screen or some mechanism by which you can enter data into your computer, right? And some mechanism by which the computer can respond back to you. That could be through audio by activating a speaker. It could be a video display where it basically turns on or off different pixels on a screen. It could be a printer where it actually prints data out onto a piece of paper, right? But all of those are the mechanisms by which the computer interacts with us. We are able to provide inputs through the keyboard, mouse, touchscreen, and various other interfaces, and it is able to respond back to us through the monitor, the screen, the printer, the audio interface, the speakers, and so on. Okay, and how exactly does that happen? How does what we want to push in go into the memory, and how does what we want to get back in response come out of the memory in a way that we can understand it, right? That's essentially the problem that we are trying to address here. So let's go back to memory, right? Because we are going to be using a trick associated with memory in order to solve this problem. Like I said, this is one particular way of solving it, not necessarily the only way of going about it, right? But it's a clean and elegant solution and is fairly general in the approach that it follows, right? What we say is, let's take a look once again at how we actually go about reading data from memory, right? And as you might recall, effectively what needs to happen is that I have my CPU, I have memory, right? These are the symbols that I've been using in order to represent these two blocks. And what I need to do is send an address. What do I mean by send an address? Physically, it would usually mean something like, there are a bunch of wires and I need to set the values on those wires to whatever numerical representation, right, corresponds to the address that I want to get, which means that there will be a set of wires, some of which would go to high voltage, some of which would go to low voltage, maybe ground, and at the end of the day they represent some ones and zeros that correspond to an address. Okay, the exact details don't really matter, but if you are interested, those are usually covered in courses on digital circuits and digital system design. Alright, so assuming that I can now send an address, right? What do I mean by send an address? Like I said, it's just activating the wires. What does the memory do? It goes up and looks up some table corresponding to whatever has been stored inside it. How does it do it? It's not like there are people sitting inside the memory, but yes, there is some logic over there, usually an address decoder, which then activates a particular row of flip-flops or memory cells inside the memory, which finally ends up by generating something in response. What is that? Another set of wires gets activated, again ones and zeros, in such a way that the CPU can now take that to be the response. Okay, so the address has been sent out, the data comes back in response. Okay, so the way that I'm saying this, like, you need to keep that in mind. I'm saying send an address, get back a response. It's not like these things necessarily take a significant amount of time. It's not like we actually go and post a letter in the post office, it then takes a few days to reach another city and then we get a response later. Over here, all of these things are happening on a nanosecond or even a picosecond scale, right? There are certain voltages that are activated that automatically causes a response from somewhere else, but logically we can think of it as sending an address, getting back a response. Okay, so far so good. How does this help us, right, to communicate with the outside world? The key thing over here is, remember that this memory, I've so far talked about it as a bag of words, some place of storing data. I've never really talked about how it's implemented, and that's pretty much beyond the scope of this course in any case, right? So for our purposes, this memory is a black box, right? The internal structure in general, we don't know how it's been implemented. Okay, so what do we do with that? What that means is, it could be an arbitrary piece of logic, electronic circuitry, right? All that matters is it has to return something useful as a response that is related to the request that we sent in. Okay, and that phrasing, that wording that I'm using here is important. Okay, what the memory returns in response to my request need not necessarily be what was put in to it previously, right? Keep that in mind. It could be anything. What does that mean? So I'm going to, anything which behaves in this way, not exactly as a memory, I'm going to use the word peripheral in order to refer to it. Okay, and the reason why we say peripheral is because we have the CPU, we have the memory, and we have the outside world. That is the periphery. So the periphery of the computer is how it then communicates with everything outside of it. So anything outside this boundary of CPU and memory we are looking at as a peripheral. Now imagine that I had, let's say, a clock, a digital clock, right? What does that clock do? At any given point in time, it has an output which basically shows the current time as some kind of a digital number, right? A set of bits. And what I do is I connect that up to my piece of circuitry which I am calling mem, and notice the quotes over here because it's no longer a memory in the same sense as what we had previously been thinking about, right? What this is saying is, now if the CPU sends out the address, let's say 42, okay, and I'm just making up these numbers, it's not that 42 has a special meaning in this context, it's just a number that I'm using at random, right? I send out the address 42, and this piece of logic out here that I have marked as mem within quotes, right, it has some kind of an address decoder. It basically matches, it looks at the number 42 and says, okay, where do I get the response corresponding to 42? It's not from a memory location, instead it just takes whatever input it got from the clock and sends that back. It responds with the current time. Okay, this is a crucial insight, right, what you need to sort of think about over here. This is how the CPU is able to talk to the outside world. As far as the CPU is concerned, it looks like it is talking to a portion of the memory, right? In practice, it is actually fetching something from outside, and that sort of switch is being controlled by this piece of logic out here that we have marked as mem, okay. So in this case, what I'm saying is, one example could be that, I try to read from address 42, what I get back is the current time. The same way, maybe I try to read from address 56 and what it responds with is the temperature, because there is a thermometer out here that's been connected up and gives back the temperature. Okay, and this piece of mem over here knows that when it gets the address 56, it should respond with whatever value it saw out here. I can generalize this obviously, right? Now we know the basic concept over here, it's easy to generalize. What I could do is I could have some other address, maybe 80, which says that, if I read from that particular address, just see whether there was a key that has been, whether a key has been pressed on the keyboard, and if so, return some kind of a number, right? After all, a typical keyboard has, well, around 100 keys, right? Usually the PC 104 keys have, keyboards have 104 keys on them, right? So all you need to do is return a number, right, which is maybe 1 to 104, right, which says which of those keys was pressed. If no key was pressed, then maybe return some other invalid code, right? Or if you have pressed shift and something else, maybe generate a new number and return that number instead. Okay. The point is, this keyboard peripheral combined with whatever is this decoding logic out here can now fool the CPU into thinking that this particular address 80 has some magic properties, right, and will allow you to basically get data from outside, right? So that's all that we need to know. Now inside the CPU, right, I can write a program where I know that as long as I read from address number 80, I am going to get back something corresponding to whatever the user typed. Okay. Similarly, I could have yet another address which takes the input from a microphone and basically converts it into a sequence of, just numbers, right? It's continuously sampling it, so to say, right? Now sampling is once again something that those of you who have done a little bit of signal processing would be familiar with. If you have not, don't worry about it. All that you need to know over here is that the audio that I am speaking out here is being sampled by a mic. There is something very fast that basically converts the strength of my speech into a set of numerical values, right? In order to get that into a computer, I need to be able to somehow read it and store it somewhere. At a very high level, that's basically what's happening, right? As long as I read from one particular address, let's say 100, each time I read, there will be a new sample coming from the microphone, right? Now, you might notice that, there are some problems there. This means that the CPU continuously has to keep reading from the microphone or it's going to lose data, right? How that is handled is, usually there are things that run in the background, there are other kinds of things that don't need to keep the CPU busy that can actually take this data and store it into some parts of memory automatically. All of that is pretty much beyond the scope of this course, in fact, but is something that you'll encounter more and more of as you get deeper into the design of embedded systems. So the bottom line is, you can make up your own mapping, right? You can decide which address corresponds to which peripheral, right? And what do I get when I read from a particular address? So this is quite an interesting sort of extension of whatever we had so far. Now let's look at another aspect of this, right? How do I write to memory, once again what I normally do is I put out an address, but the next thing I do is I am not waiting for the memory, I then send it data, right, and that data is supposed to get written into some location inside this memory normally, right, but of course over here I have this interesting new type of memory, right. What happens instead is that this data will just get passed through to something else. Which thing? That depends on what address was sent in the first place. So supposing I give an address corresponding to something on the screen, right. So this screen after all can be thought of as some kind of a, you can think of it as a graph paper, right, and what do I need to basically put into this particular dot or this particular dot or this particular dot or this particular dot. Each of those dots can be given xy coordinates which can be combined together in order to generate an address, right. I finally generate one number that basically says, okay, this corresponds to this particular dot on the screen, right. Obviously the dots are much smaller than what I am currently showing, but logically you can think of it that way. Now if I have an address for each dot on the screen and I send a number, right, that number can be translated into, should the dot become, should it be turned on, should it be turned off, are there three different colors RGB, red, green and blue, how should they be activated on that particular dot, okay. And by so doing I can literally sort of turn on and off each and every individual pixel or picture element on the screen and thereby build up this entire image that you see in front of you, okay. If I instead sent it out to a printer, then the printer probably has some extra logic in there which basically says, okay, the letter A came in, fine, translate it into this set of ink dots that finally show up on the screen, right. If I send values continuously out to a speaker, right, just like I was able to sample from the microphone and get numbers into the computer, I can send those samples out to a speaker, activate that speaker, make it sort of vibrate back and forth and produce sounds, okay. I could further take some of this data instead and maybe save it somewhere else or send it out over a network or store it onto a disk, right. All of these are things which will become more obvious when we start looking at actually using those kind of peripherals. The bottom line is we have once again used exactly the same trick, right. We fool the memory by giving an address, or rather the memory fools the CPU into thinking that it has taken this data and stored it in an address, whereas what it has actually done is sent it out to some peripheral or the other, okay. And this data basically gets sent through. In fact, the interesting thing over here is we can even reuse the same address as what we used for reading, because remember that if you go back and look at this, when I read from address number 42, right, it doesn't really tell me that this number, it just gives me back the current time. So what would happen if I wrote something to address number 42? Bottom line is this part of the circuit doesn't say anything about that at all. It doesn't tell you what needs to be done. It doesn't say that I need to go and change the time on the clock. If you wanted it to change the time on the clock, you need to change your circuitry here so that it would actually send some data through to a clock peripheral and cause it to update its current time, right. So address number 42 could be used in order to set time on the clock, but it's not obvious that it is always going to do that, right. I could very well even have that address number 42 actually causes something to be drawn on the screen, right. The bottom line is the combination of these two approaches has allowed us to sort of build up something that can communicate with the outside world, right. There was this CPU, this little box out here whose only job is to perform computations. That was then expanded by basically allowing it to talk to another box out here which we said was memory. Now this memory is suddenly allowing us to talk to something else which is the outside world, right, and that is a tremendous expansion of the capabilities of what a CPU can do. So let's once again look at the structure, right, of what a CPU is, right. We have this box out here that performs computations. It can send in addresses to this other big box out here, right, that we are calling memory, right, and this one basically takes in addresses and we could either write data. I am calling it data out because from the point of view of the CPU this is an output. It is something that I am sending out of the CPU. So it's the data out coming from the CPU, going into the memory, either getting stored in the memory or being sent through somewhere else, right? To start with, at least what we had was that, anything that was being sent in over here on the data out would get written somewhere into the memory, right? And instead, if we were performing a read, then what would happen is I would send an address and I would get back data on a data in, right? So data out and data in are logically different sets of wires. Physically, whether they are different sets of wires, that depends on the CPU and how it is actually implemented, right? It is not absolutely necessary that they are physically separate, but logically at least they are distinct. What you send out and what you get back in follow different paths through the system, okay? So in normal memory, in other words, when I write something to address number X, I can then read it back later and normally be assured that I will get back whatever I wrote, okay? What that also means is I could then use that in order to store code, the data corresponding to that code, some more code corresponding to another program, right? The data corresponding to that program, and so on, right? You might be thinking at this point, why would I have multiple programs in the memory at the same time, right? There are a couple of different possible reasons for this, because after all there is only one CPU. It can only be executing either code 1 or code 2 at any given point in time, right? And that's absolutely correct. In practice, of course, what ends up happening is, remember what the CPU can do, it can do whatever it does, it can do extremely fast, right? So one thing that could be done is I could basically say, hey, I'm just going to finish this entire program 1 very quickly, and then I'm going to switch over to program 2 and run that, and then program 3 and program 4 and so on, right? So rather than sort of loading in new programs and data from somewhere else every time, I will assume that they are already present in memory and just execute them one after the other. The other way of doing it is, I actually spend a small amount of time running the program 1 and then just stop without finishing it, jump to program 2, run it for some more time, I don't wait for it to finish, I jump to program 3, I jump to program 4, and eventually I come back to program 1, okay? How does this work? Because I can do this on a time scale of milliseconds. Let's say that I decide to run program 1 for 10 milliseconds and the clock speed of my computer was 1 gigahertz, right, 1 nanosecond clock period. Basically means that within 10 milliseconds I could run 10 million instructions, 10 million clock cycles have passed. That's quite a lot, okay? I can actually do something useful within that time. But as far as human being is concerned, 10 milliseconds is much less than the blink of an eye. The blink of an eye is literally around 100 milliseconds or so, right? So within 10 milliseconds you do something with program 1 and then you switch over to program 2, the person, and let's say you do a few of these and then you come back to program 1, the human being doesn't even know that you have actually done all of these things differently, okay? How does that work? And all of that, yes, you need to get into a lot more detail in how programs are written, how concurrency is handled and so on. There are other issues that come up there, right? It's a more advanced topic. It's just good to know at a high level at this point. Hopefully, you will be doing courses that handle this in more detail. It will not be covered in this particular set of videos at least. Okay, so apart from all of that, right, at the bottom of the memory, I have marked this thing that I call peripherals. And in a peripheral, if I write to address X, the effect may be external. That is to say, if I write out to P2, chances are that it's not just storing a value somewhere in a physical location out here, it's actually maybe drawing something on the screen or writing to a printer or just causing a blip on a speaker, something of that sort. And when I read back from X, which may or may not be even the same address, right, or rather if I read from the same address X, in fact, there's every chance that what I get back is not what I wrote to start with. It might be something completely different, okay? So I could read back, I could have these input peripherals that basically respond in a totally different way than what the output peripherals handle. So let's try and sum up everything over here, right? What is a computer after all? The core unit, the most important part as we saw, was this ALU, the arithmetic and logic unit. Now, for various reasons, primarily to do with the physical aspects of actually building such circuits, we were able to justify that we also need a set of registers whose job is to act as a temporary memory sitting very close to this ALU, right. So these registers basically act as something that can just store some values very close to the ALU in such a way that the ALU can perform operations using the data from those registers. And when we put these two together, we call that a CPU, right. Now a modern CPU probably has a lot more than this, right, but if you go down to the core and ask, okay, what is it actually doing, this is pretty much it, okay. It performs computations on data that is present in registers, right. That's basically all that you need in order to build a CPU. Now in order to do something useful with it, you need to augment it, right. That CPU by itself can't get any useful information into it or out of it. So you provide it with a bidirectional link, right, to some kind of memory which is used for storing data, right, and that memory essentially has the ability that we can write into it, we can read back from it, and if I have instructions, data, everything present in that memory, then I can do something useful with it, right. I can also, what the CPU can typically does is it has this thing called the program counter, which sends addresses out here and starts reading out the code instructions one by one, and those code instructions in turn say things like, okay, load data from here, right, perform certain computations and store the data back into this particular location, right. And what we can see is that memory itself is further augmented by having another part which we once again relate with the memory in the sense that it is part of this same addressing scheme, but now this talks to the outside world, to the peripherals, okay. Now let's try and summarize all of this, right, very quickly. What I have put over here is just a picture of what's called a motherboard, right, and hopefully by this point most of you have at least tried opening a computer and looking inside it. If you haven't, please do, right, because that's a crucial part of actually, that curiosity is important, right. It's all very well to say that I'll use a computer as a black box, but it's always good to know a little bit more about what's there inside it, right. Now this is a picture that I have taken from Wikipedia. It's just a very a bland picture of what we would normally call a computer motherboard, right. I don't know what exactly the model of motherboard or anything it is. In fact, as you can see over here, right, there is this green part out here is essentially what's called the PCB, the printed circuit board, okay, and that's sort of the basis of on top of which all the other electronics are assembled. All these things that you see over here are actually not the chips, they are not the sort of functional parts of the computer, they are only the interfaces, they are actually the connectors and nothing else, right. So most of them are just pieces of plastic with appropriate sort of metal wiring underneath them. All of these metal wires, you can see that there are a lot of metal wires out here, they are used in order to connect the different things, and if you look at the PCB itself, the motherboard, you will see that there are a lot of traces or wires running around on that motherboard connecting the different parts together, right. This only starts to get useful when you actually put certain other components, right, the chips that people have designed into this motherboard, right, and actually start populating it and making something useful with it. And by looking at this motherboard, one of the things that we can say is this part over here, right, is typically the socket where the CPU, the central processing unit, actually gets planted, right. It's the thing that actually performs, so all the parts, the ALU registers, everything would be encapsulated into a single chip and would finally get placed on this particular location. If you look closely at the motherboard, you will see that there are a lot of different metal points of contact over there, right, which basically when the chip is actually placed over there, all the metal contacts are able to perform, are able to create conducting paths into the interior of the chip. The voltage, which again is provided by the power supply of this motherboard that's connected to this motherboard, will finally get through into that chip, activate it, and whatever the signals that are being generated by the chip will then come out onto those wires and they can then be sort of addressed by various other parts of the system, right. Now on this motherboard there are actually a whole bunch of different connectors and peripherals that are potentially useful. The one important thing that you can sort of identify is these sockets out here, right, the sort of black things that are present. These are typically what are called the memory sockets, right, for DIMM modules, the dual inline memory module, right. And the DIMMs are the, usually what happens is you have like multiple different components corresponding to a chip, right, all of which then needs to be placed on the particular location, right, into the socket, and combined they essentially provide a memory block. Apart from that, what we have is peripherals, right, peripheral interfaces rather. So this particular socket over here is for audio, right, a microphone as well as a speaker or a headphone. Keyboard and mouse get connected here, USB gets connected here, there are a lot of PCI interfaces out here, right, which are used, for example, for things like graphics cards. Those of you who play video games might know that, you know, having a graphics card allows you to get better video, right, and more sort of fluid graphics. That's basically where it fits in, right. Why do we need a graphics card? All of that is sort of beyond the scope of what we will be doing in this course, but if you think about it, ultimately all that those things are doing is saying that, okay, if the CPU cannot do something fast enough, there will be some part that does a specific kind of function even better than what the CPU can do. So that pretty much summarizes our understanding of what the different components of a CPU are and how in fact a CPU performs its function, right. From here, what we would like to do eventually is to take it forward and say, okay, how do we then go about programming a system? And eventually, you know, one of the main things that we wanted to do over here was to understand why we need to understand the C programming language and how it helps us with all of this. Okay.